Geology section, and we're first going to answer the question of what is the mechanism that causes plate tectonics. Then we're going to move on to talk about a few other basic things that you need to know about geology that affect the ocean. All right, the simple answer to the question how plate tectonics worked is a motion called convection. Convection is basically the idea that hot fluids, and fluid is basically any kind of connected mass. It could be air, it could be water. In this case, it's more or less the mantle, which is kind of a plasticky rock, that hot rises and cool sinks. Most of us sort of know this already. If you have a radiator in a room, which we really don't have a lot of here in the Southwest because we don't really have to heat our houses, but if you've ever been around a radiator, the warm air rises, it travels across the ceiling. Now that we do know. If you've ever gotten up on a ladder, you know that it's hotter up at the top of the house, up at the top of the room, than at the bottom, and that's why we only have single floors basically in the Southwest, because the second floor would be too hot to use. But then as air cools, it sinks back down because it becomes heavier, and then it's pulled over to the radiator again. HVAC people understand these circulating things pretty well. Another way to think about it is if you open up an oven, does the hot air, rise up into your face, or does it sink down on your feet? And if you open up a refrigerator where the freezer is on top and you open the freezer up, does the cold air rise up to the ceiling, or does it come down on your face? So basically, hot rises and cool sinks. Now, I want to show you this quick little video of what I just said by a very cool Scottish geologist.
Rock rises.
Oh, wait, no.
Rock rises,
heated by the Earth.
It happens because hot rock rises.
It happens
heated
because
by the
hot
Earth's
rock
core.
rises, heated
Near
by
the
the
surface,
Earth's core.
the rock spreads in two
Near the
directions
surface,
and
the
goes
rock
sideways.
spreads in two
It
directions
begins to
and
lose
goes
heat.
sideways.
Eventually,
It begins
the
to
much
lose
cooler
heat.
rock sinks
Eventually,
back down.
the much cooler rock
Through this
sinks back
spreading
down.
process, the Earth's
Through
crust
this
is very
spreading
slowly
process,
dragged
the Earth's
apart.
crust is
So this would
very
be
slowly
an
dragged
illustration
apart.
of the spreading ridge that we talked about last time.
And it's this that ultimately causes the
And it's this
continents to
that
move.
ultimately causes the continents to move.
Where the plates collide, the rock on the
Where the
seafloor
plates
containing
collide,
carbon
the
from the
rock
dead
on the
plankton
seafloor
is
containing
carried
carbon
deep into
from
the
dead
earth.
plankton
Okay,
is
here's a
carried
subduction
deep
zone.
into the earth.
This would be an oceanic trench. We're assuming that there's an ocean on this.
As it descends, this layer of rock is heated,
As it descends,
so the
this
rock
layer of
melts,
rock is heated.
releasing carbon
So the rock
dioxide,
melts, releasing carbon dioxide.
and gas is returned back into the atmosphere
And gas
during
is
an
returned
eruption.
back into the atmosphere during an eruption.
The remarkable cycle is complete.
The remarkable
And it
cycle
is a
is
remarkable cycle. We'll talk a little bit more about the carbon dioxide part of it later. Okay, now I might not always show you all the little video links in here, but they're available. So if you want to look at them yourselves later, they're always in there because they're very useful. All right, so let's talk about continental versus oceanic crust. They're called this basically because continental crust is the stuff we can see. It's the rocks on the surface, and the oceanic crust is the rocks underneath the ocean. So how do they get that way? Well, we're back to density again. I talked about density earlier when I said in the cosmogony section that our planet is still hot and it has stratified according to density. Again, kind of like a stew, right? The heavier stuff sinks to the bottom, the lighter stuff floats on the top. We're floating on the top. So we are up here with the crust. So what the rocks we see up here are basically the light fluffy rocks, the less dense rocks, all right? Again, density is mass divided by volume. Now, this is supposed to be a model of the Earth with the ocean stripped away, so that you can see that the continental rocks, which would be these continents, right, are higher than the ocean rocks. Well, we kind of knew that already, right, because otherwise they wouldn't be sticking out of the water. But why are the oceanic rocks down like that? Again, it comes down to density. Think of the mantle underneath the Earth not as something hard and unmoving like we sort of think of the Earth is sort of most of the time, but as more like a jello. And I'm holding in my hand here sort of a little steel ball and a normal rock. They're about the same size, but the steel ball is considerably heavier. It's more dense. It's got more mass per volume than this rock does. So if I drop them both on a layer of jello, the steel ball would sink down lower. So that steel ball would represent oceanic crust. It's heavier, it's denser, and so it sinks into the mantle lower. And because it's lower, naturally when the water accumulates, it's going to accumulate in the low places. And so we call that kind of crust in the low places oceanic crust, because it tends to have oceans on top of it. All right, let's move to, I think the last subject on the Earth I want to talk about is magnetism. Very, very important, because without our magnetic field, there would be no life on our planet. Life on this planet evolved about the same time the magnetic field did. This is an illustration of a magnetic field. Basically, it's invisible. A force field essentially that is electromagnetic, meaning it's got an electrical component and a magnetic component. We're not really going to get into the physics of it, but they're both wave components. It's actually not all that strong. Down at the bottom there, I wrote down that a refrigerator magnet has about 50,000 microteslas. That's how you'd measure magnetism. And the Earth's magnetic field at any point is only about 30 to 50. So that's what? 1,000 times. Your refrigerator magnet is 1,000 times more powerful than the Earth's magnetic field. But your refrigerator magnet is not causing life to be possible on this planet. Okay, so anyway, electromagnetic field has an electrical component and a magnetic component. It's one of those four basic forces that I said were created in the first second after the Big Bang. Important stuff, right? And it's dipolar, meaning it's kind of like a battery. It has a positive end and a negative end. In the time period we live in right now, which we call normal polarity, because for us it's normal, the positive ends on the North Pole and the negative ends on the South. And so the field lines are coming out of the planet from the bottom, and they are going into the top of the planet. So they're going from south to north. Now, why it's so important to us. We talked about the fact that the sun is essentially a living fusion bomb, right? It's fusing hydrogen and hydrogen together to make helium, which is letting out tremendous amounts of electromagnetic radiation. If it wasn't for the fact that we have an electromagnetic field, it would blast away our atmosphere, and then our oceans would boil off, and we would have just a dry, empty planet. Okay. This illustration here, there's the Earth, right? The little tiny Earth. And this is showing the electromagnetic field waves. They're being distorted as the solar wind comes at them. But basically, what they do is they direct them around our planet. I mean, they still get through. You know, sunburn is a radiation burn. It's not a heat burn, right? It's a radiation burn. So, you know, there's still plenty of radiation that gets through. But not enough to kill life on this planet, unless, of course, you were staked out in the desert, which we don't want to talk about. How did I even get on that subject? So we believe that the Earth's magnetic field formed on this planet approximately 3.45 billion years ago. And that's approximately the same time that life started being fossilized on this planet, that we've found evidence that life became situated on Earth. So how do you make a magnetic field? You need three things. You need metal that is liquid and rotating. If you have liquid rotating metal in the core of in the center of your planet, it'll create a force field, an electromagnetic force field. Actually, it's the same principle that they use to make alternators in your car. It's a spinning coil of, it's not metal, liquid in that case, it's a spinning coil of wire, and it generates electricity. But there's a little video here where some scientists did an experiment where they kind of created their own mini planet to see if they could make a liquid rotating core. Would it create a magnetic field? And it did. It was really kind of neat. So if you want to see that, it's only a couple of minutes long. Let's see, what else did I want to tell you about that? We have magnetic reversals. Now that's strange, right? What does that mean? That means that what's normal for us, which is that, and compass needles, compass needles work on the principle that there's an electromagnetic field. They point in the direction that the field lines are going. In that case, right now for us, that's essentially north, a magnetic north. It's not the perfect top of the planet. It's where the field lines go in. But every so often on our planet, and there's no pattern to it, the field reverses. Not abruptly like that. It takes some time. And in that case, if you lived during that time, compass needles would probably point all over the place. But sometimes it reverses and it goes the other way. And this flips back and forth a lot during geologic time. So we call that reverse polarity. This is a picture. This is representing time and polarity, magnetic reversals. So over here, down here, this is 4 million years. MA is million years. Down to the present. So I guess the dark line means normal polarity for us. And then you can see the light lines mean reversed polarity. So you can see, sometimes there's a really long time of normal and a short time of reversed. But then here's a really, really short time of normal and a really long time of reversed. And you can see again, there is no pattern to it. We don't really know why it happens. These words here, these are geologic names for time. Geologists don't name time in like millions or billions of years. That wouldn't make sense for such long periods. We name time periods for important things that are happening geologically on the planet. Okay, so the reverse time periods are called chrones. They might be called anomalies in your lab. You're doing a lab on this magnetic, well, no, you're not. You're not. Never mind that. You're doing a lab on plate tectonics. So, how do we know this? Since, let's see. Let me see. When was the last change? 0.78 million years ago. That's 780,000 years ago. There were no people here. So how do we know that it changed, right? Well, this is supposed to be the mid-ocean spreading ridge. The magma's coming up in the center. There's our mid-ocean spreading ridge, our mountains. And we're making the rocks for what we call normal polarity, brown. And we're making the rocks for reverse polarity, blue. And so this is 0, right in the middle, present time. That's 1 million years ago, 2, 3, 4. They'll be about even because the spreading rate is probably pretty consistent. It speeds up and slows down a little bit, but it's pretty consistent. All right, so how do we look at the rocks and know that it's reversed or not reversed? Well, if you take a geology class, you'll end up looking at a mineral called magnetite. Magnetite is magnetic. Magnetite when the crystals are forming out of the magma, they will align themselves with the magnetic field. They'll point basically in the direction of north. So you got these little mini compasses basically in the rock record. The rocks tell us an awful lot about the past that we would otherwise never know. Geology is cool. So basically what this is, this also, you know, adds more evidence to the theory of plate tectonics, right? Because we noticed that 1 million years ago on this side of the spreading ridge, because this backs up spreading ridges, 1 million years ago, it looks like there was normal polarity. And the same distance away on the other side of the spreading ridge, if the rocks were being created and moving apart at an equal rate, the same side on the other side should have the same kind of polarity, right? So it looks like it's normal on that side. And then 2 million years ago, it looks like it's changing to reverse. And over here, 2 million years ago, it's changing to reverse. This is sort of the same, well, this is the same thing represented a different way. These wavy lines, if they're up, it means what we call positive or normal polarity. And if they're down, it's reverse polarity. Or here's another picture of the mid-ocean spreading ridge. It's cracked, right, because it's a plate boundary. This side is moving that way, this side is moving that way. And there's, instead of normal and reverse, they're putting positives and negatives. And so what you're seeing here is, again, lines of rock that have moved apart from the spreading ridge. The lab you're going to be doing is exercise 3 on page 47. You're going to be calculating some, you know, distances, how long it takes. Let me look at this. We've got a spreading ridge, and then they give you a bunch of points, and it looks like you're probably going to have to measure how long it is. You may need a ruler to see how far it moved, and you're going to, they tell you. They tell you how far it's moved in kilometers. They tell you how old the rock is in years. And all you have to do is figure out, down below it'll say, like, from A to B, how fast was it spreading apart? Well, how do you do that? You measure how far the distance was, and then you divide it by how many years that was. And since they give you the years of the different points, all you have to do is subtract to figure out how many years it is. They want the average basin expansion rate. Average basin expansion rate. I'm not sure how that will differ from... they want to see if it's speeding up or slowing down. So, you know, at whatever point you're at, you know, you might be measuring just from here to here and find out how fast it's going, but they want to know overall how fast it's going too. That would be the average, and then you're going to compare the two. So it should be pretty straightforward. You are going to have to convert kilometers to centimeters. That's a very easy conversion. Hopefully you got the conversions in the math week. If you have any trouble with that, you know, there's tutors for math in the Student Success Center. You can always contact me, but an easy conversion like that you should definitely be able to do, because I'm sure they will show up again, stuff like that, on the test or the midterm or the final or all three. All right, until next time. Oh, wait, I did want to show you one more thing. Never mind about next time. Not next time yet. I wanted to show you this little animation, if I could find it. Where'd it go? Be here. Continue recording. Oh, I don't have it anymore. All right, then I'll just have to find it the hard way. Control C. Let me put it up here. Control B, because this is a pretty good little animation. All right, so I'll bring it over here. So, good illustration, right? This is supposed to be magma coming up to the mid-ocean spreading ridge. This is the mid-ocean spreading ridge. The dark means normal polarity, where north, this is our little compass needle, it's going to flip when polarity flips, is pointing north. The white rock means that the polarity was reversed, and so then south would basically be north, right? Down here, we've got age in millions of years. It's going to start 5 million years ago and go to the present. Again, these are just names of different geologic times. So, it's a good example of subduction because you see it subducting on the right-hand side, and about, you know, that 40, 50 miles from the trench, there's the volcanic activity because the rocks are melting and the less dense things are coming to the surface. I do want you to notice that there is no pattern to the reversals. We have not ever been able to find one, and we do not know what causes them. It'd be neat for someone to discover that in my lifetime. I would like to know that, actually. And I do believe that concludes what I wanted to tell you. Yes. All right. Until next time.